Hey everyone, let's go get started on our noon session here at the first Geotech Center Virtual GIS Day. Here on the slide, you can see a lot of information about the Geotech Center and what they do and the kinds of professional development opportunities and geospatial initiatives that they offer. So check out that website. And all of the other Geotech Virtual GIS Day activities are there on the hub site in the top link. So I'm Lisa Stanish. I'm the moderator for this session. I'm here at Lakeland Community College, about 25 minutes outside of Cleveland, Ohio today. And today's presentation is going to be offered by Rick Toomey. He's a cave research management specialist at Mammoth Cave National Park. And in this capacity, he facilitates research at the park, works on planning projects, and implements cave resource protection. He's conducted research and participated in exploration and mapping of the caves in the park since 1994. So that's what he's going to share with us today. So I'm going to stop sharing and he can join with his presentation, and we will be taking questions in the chat. And we will ask them at the end of his presentation. So feel free to put them in and we'll compile them and get to all of those at the end. So thank you very much, and I'm going to stop sharing.
Okay. Let's see, still need to get that into display. Okay, are we good on the display currently? Good. Okay. As Lisa noted, I'm the cave specialist at Mammoth Cave National Park, and I'm going to be talking today about mapping of caves and some of the key maps in the history. As my title says that I'm going to be talking about 6 maps. You're going to see probably 30 maps, but 6 of them are historic maps that we're going to be focusing on. Mammoth Cave is located in central Kentucky, and the small purple line is the mapped extent of Mammoth Cave. It is currently the longest known or mapped cave in the world. If it's not documented, it doesn't exist. So we mapped the cave. Currently, there are 412 miles of mapped passages, and some of them, about 30%, actually go outside of the park, as you can see in this map. This is a map of an area around our hotel and visitor center area. The cave is shown in this red and blue, but we've got roads, we have buildings. The bright blue lines are our sewer lines. So one of the reason we map the cave is to know where it goes, to understand it from a scientific standpoint, but also from a management standpoint. We need to know where the cave goes, how it relates to the surface features, because we can't protect it from like sewer breaks if we don't know what part of the cave a sewer line break might be. So I'm going to start with some info on how we map the caves. Mapping the caves is actually a fairly simple kind of mapping, and it's actually not that different than surveyors mapped things prior to GPS. We do sequential determination of spatial relationship between points when we proceed from point to point through the cave, because there's no access to GPS in the cave. The signal is just really, really bad. The other problem is you can think of normal surveying methods, but sometimes you're going through a tube the size of your body that is half filled with water. This is a small section of cave map from Mammoth Cave. The blue lines are showing survey lines from point to point to point to point. And the rest of the map shows features that have been hand drawn by a team in the cave. On a fairly simple cave, A cave survey might look like this. You go from station, you start your survey at station 1, move to station 2, station 3, station 4, station 5. At each station, the data you need, we need a distance between those stations. We need a horizontal direction between the stations. We need a vertical direction between the stations. And we also take passage dimensions, how wide the passage is and how tall the passage is at each station. To get this data, we have a variety of different ways. For the distance between the stations, the old standby is a fiberglass tape. A very useful way, you just stretch it between the points, read the tape, and find out how far apart the points are. This is durable, it doesn't break down, you can drag it through the mud and it will still read. We do also sometimes use laser distance measuring tools. Those give you a nice accuracy. They're very quick. They're very compact, but they don't like water and mud quite as much as a fiberglass tape does. So we are sometimes limited on where we can use those. For the horizontal direction between stations, we have, again, a couple of different ways. Most commonly, we use an azimuth, reading an azimuth through a sighting compass, such as this Sunto compass. We do also have some all-in-one laser distance things, which will read with just one click. It's a standard Leica, but it has had new materials and boards and sensors added to it that allow it in all-in-one to read a distance, a azimuth, and a inclination. Again, these are expensive and they're electronics, so not as much of the cave gets surveyed that way. Most of the cave we still survey using a manual sighting compass. The vertical direction between the stations, we use a inclinometer, similar to what you might use to estimate the height of trees in forestry, or we can use the all-in-one thing, or Disto X as we call it, as well. In the passage dimensions, we estimate or measure at each survey station the distance to the left wall, the distance to the right wall, the distance to the ceiling, and the distance to the floor. And that will give us essentially a box of the size of the passage, let you know to some extent how large the passage you're working in. But how do you know in a situation like this that you're getting the right answers? Well, that comes down to quality control. The first thing we do with quality control, we actually do front sights and back sights on all stations. We measure from station A to station B, and then you measure back from station B to station A, and you compare the front sight and back sight, azimuth and vertical angle, make sure they're within within 1 degree of in agreement, and that is one way. Then, while we're in the cave, we are actually plotting the survey and doing a scale sketch of the cave. So when your survey book seems to say you're making a left turn, and you can see standing there, you're making a right turn, then something's gone wrong with your measurements. So that can be used for identifying errors. And then we also do loop closures. In a cave that's 412 miles long, you will make thousands and thousands of loops. And you can do the math on these loops to determine when you do a big circle around a thing, the point that you started and ended with should end up in the same place. And so loop closures are a way to of quality control. So how do we do this? We do these with teams of approximately 3 people, sometimes 4. One person is holding the tape, putting a light on the station for the person to sight to, pulling the tape for distance, choosing those stations. A second person has the instruments, is reading the azimuth, is reading the vertical angle. They report that to the third person. That third person is recording the data, verifying the agreement between the front sight and back sight, and making a field sketch. Essentially, they are mapping the cave in the cave. It's very much like old plane table mapping, if you're familiar with that type of survey, where you actually end up drawing your map while you're out in the field. Those individual maps are then given to a cartographer who manages the data for those for certain sections of the cave, and then they draw up the map. They take that sketch, use scans from that, and then draw it all to unify the look of the map. They don't add data, they don't take data away, but they make it all unified. Here's what a field notes might look like. Station from G6 to G7, 67.3 feet, 276 degrees at -4 degrees. For some reason, they don't have a ceiling and floor height. I'm not sure exactly why in this particular case. And then these are field sketches that the person made. Essentially, it's the rough draft of the map. And it's actually the rough draft of this section of map right here. So that's what that ended up looking like in the final map, part of the historic Mammoth Cave quad that Ed Klossner has been drawing up. Now we'll take you through some history of mapping at Mammoth Cave. The first map is a map called the iDraft map. It is from 1811. There are 3 known versions. It's actually not it's a sketch, not a survey. The entrance to the cave is shown down here. This is a map that was basically built to show the extent and location of nitrate deposits in the cave, say saltpeter. And it was essentially for advertising to the saltpeter, to the people who needed saltpeter to sell them on buying saltpeter from Mammoth Cave. And this is from the Hagley Library in Wilmington, Delaware. Another one of the copies is in the DuPont archives because the DuPont company was one of the early buyers of saltpeter from Mammoth Cave. It shows a portion, it shows probably roughly 8 to 10 miles of cave passage. And it really is just a diagram of those passages. The next map is the first really surveyed map that we have of Mammoth Cave. It was done in 1835 by a professional surveyor. His name was Edmund Lee. It's a compass and line level. It was done over several months in 1834 and 1835. It shows both the passages in plan view, and it shows a profile, a running profile of the various passages as well. it served two purposes. One, it was a map that the Mammoth Cave owners requested to be done so that they had a good map of the extent of the cave. However, it also was an advertising tool for Edmund Lee. He was working on trying to get more jobs, especially jobs working with surveying railroads, and thus surveying the cave and showing the profiles was a good advertisement that he people to show his skill in being able potentially to do railroad surveys. At that time, this is the extent of the known passages of Mammoth Cave. The yellow, I'm going to show a number of these at different times. The current known passage extent is in the yellow, and at that time, this was the known extent based off the Lee map, this red over in this segment. Salt's Cave was also known, but that's not part of the mapping at that point, at this point. The next map, it was a very interesting map, Stephen Bishop's map of 1842. Stephen Bishop was an enslaved African American. He was brought to the cave in 1838 by his master Franklin Gorin, who owned the cave. He guided tours and he explored the cave. In 1839, he was actually sold with the cave to John Cron. In 1842, John Cron had him draw a sketch map of the areas that he knew of the cave. They gave him a copy of Lee's map and then told him to draw what he knew off of Lee's map. He drew this sketch map of the cave as explored in 1842, and it was included in an 1845 book called Rambles in Mammoth Cave by Bullitt, and essentially was advertising for tours at Mammoth Cave. It shows an estimated 20 miles of cave. You can see the areas that Bishop found that were beyond the areas that Lee had, that were known at the time before Bishop came to Mammoth Cave. So he actually may have been the person in history who individually found the largest amount of unknown passage in Mammoth Cave. He certainly has found some of the most important passages in Mammoth Cave, yet he was an enslaved African American. He was freed. He got his freedom. Unfortunately, but he continued living at Mammoth Cave and continued guiding as a freedman. But about a year or about 2 years after he got his freedom, unfortunately, he died. The next map is a 1908 map. It was done by a German engineer named Max Kemper, guided by Ed Bishop. Ed Bishop was Stephen Bishop's grandnephew. Kemper was interested in Mammoth Cave because there was an earlier German engineer who had done a map of Mammoth Cave. Well, he came here to look at mining techniques and mining equipment for his family's business. He also wanted to come and see Mammoth Cave that Max Eit had mapped in the past. He was hired by the manager of the cave, Albert Janin, to map the cave. Ed Bishop guided him on this tour, He mapped for 8 months in 1908. This is a fully surveyed map, probably with compass and tape. It interestingly has no north arrow or scale on it. And the reason but it does have some register marks that we think were related to an overlay that might have had those things on it. This map was kept secret as well. All of these things are related to the fact that this map clearly showed that Mammoth Cave went off the property owned by the Mammoth Cave estate. And the estate wanted to use the map, but didn't want people to know that the cave went off the property. So they were not going to create a map that had a scale that allowed people to see exactly how far the cave went off the property. It shows approximately 35 miles of Mammoth Cave, this area in here. It was lost, but was refound in the park's archives in 1963. This version that I'm showing you here is a recent digital restoration of that map. The next map moves up to 1964. This is a surveyed map by the Cave Research Foundation. And this was a folio book, a folio map with a variety of different quads. The Cave Research Foundation began mapping in Mammoth Cave in 1957. They started working in a section called Flint Ridge. By the early 1960s, they connected Salt's Cave, Crystal Cave, Unknown Cave, and Colossal Cave into the Flint Ridge cave system. This map shows the extent of the Flint Ridge cave system in 1964. It shows 55 miles of passages. At the time, that was actually the longest cave in the world, divided into 30 quadrangles. I'm going to zoom in on one of those maps. This is the Crystal Cave quadrangle, showing the size of passages, where they go, but notice there's really limited detail on what's in the passages. At that point, this portion over here is Flint Ridge. This is the extent of the Flint Ridge system when the folio map was made. The Mammoth Cave system, this was around, as we said earlier, this was around 45 miles. This is 55 miles. So the Flint Ridge cave system was longer than Mammoth Cave and was vying for the longest in the world. In 1972, the Cave Research Foundation mapped a connection right here between the Flint Ridge system and the Mammoth Cave system. Since 1962, they had also continued mapping in both Mammoth and Flint Ridge. So at that point, it ended up, when these were connected, they became they measured 144.4 miles, completely making it without a doubt the longest cave in the world, and it hasn't looked back. Now, a current modern Cave Research Foundation historic cave quad. Again, the cave is so large that in order to map it at a reasonable scale and show reasonable amounts of detail, you can't just put it all on one sheet, so we have it divided into quads, something that the folio map did as well. We've increased our standards for our cave mapping. One, we have better horizontal and vertical control. The original, many of the original maps didn't have extensive vertical control. They just assumed Mammoth Cave is pretty flat, so it didn't really matter the vertical control. Now we use very good vertical control. We increase the amount of detail that we show in the passages, whether that's water in the passage or rock fill or where a trail goes. We've really increased these. We have Ed Klossner is the cartographer on that. He does this purely on a volunteer basis. The extent currently of Mammoth Cave is about 412 miles. There are 27 current entrances and 3 collapsed entrances in this 27 miles. This is 412 miles. So we have a very extensive set of mapping. This shows the extent of the Cave Research Foundation's quads and their index of quads as of 2020. We have a chief cartographer named Bob Osborne. He manages all of the maps and the mapping and all of the different cartographers. We have about 15. We have about 15 cartographers. The data ends up. We have a data manager for Flint Ridge. We have a data manager for Mammoth Cave Ridge. We have a data manager for the river segment, and we have a data manager for Roppel Cave. Those data managers make sure all the data is unified, feed the data, which will be both scans and reduced line plot data that is reduced for vertical and for vertical distances. We have all of those 27 entrances as high precision GPS fixed points. In the Mammoth Cave Ridge section, we also have a older 1936 USGS survey through the toured trails that has benchmarks in it to allow us to have additional fixed points. These fixed points give us where are we in the world, and then the cave survey connects those and gives us the survey network. The survey net then gets exported. Most of the maps are, most of the cartographers, all of the cartographers are volunteers. The cave gets mapped in approximately 10 expeditions. There are weekend expeditions and 1 week-long expedition each year. The cartographers send objectives for the expedition, say, I desperately need somebody to go out in this little passage over here. There is a lead off to the side that has never been mapped. Someone needs to go and get that. The cartographer will tell you whether they need wetsuits, whether they need to be able to ascend and descend ropes, whether they need to, whether there's a size limit to how big they can be to get through particular crawlways. So the cartographers will manage that data, send it to the expedition leaders, who will send out teams of 3 to 4 people who will go and do these objectives. The objectives then feed the data back to the cartographer, so the cartographer can continue the mapping effort. So where to next? We are continuing our quad mapping. We continue to find passage in Mammoth Cave at a mile or more a year of new mapped passages. We continue to upgrade some of the survey in areas that have not been resurveyed. For instance, some of our survey in Flint Ridge is still from 1960. So we need to get people back to upgrade that survey, check those. We've experimented some with LiDAR mapping in some of our larger passages, some of our toured passages. LiDAR units are very cool, but they end up having large data sets that have to be managed. And again, they're not really wild about wet, muddy areas either. We've got people working trying photogrammetry for building cave passage representations and cave passage maps. We continue to use our line data in management of the cave, and we continue to do find additional caves on the park. I mentioned that we have Mammoth Cave on the park, and it's 412 miles long. It's actually only one of over 500 caves on the park. Some of them are 30 or 40 or 50 feet long, but we have portions of a 114-mile long system. We have portions of a 35-mile long system. We have caves that are 7 miles long. We have about 12 caves that are over a mile long on the park. And all of these need to be mapped. All of this mapping data we convert to GIS, so we can use the data to understand how the caves developed, to understand where the caves go, what caves might connect to each other, but also what impacts we might have with the caves, and how we need to protect them from ongoing potential issues. So that's where we are at Mammoth Cave, and some of the history of the mapping here at the park. And I'm happy to take any questions that might have come in. Lisa has questions from the group.
Okay, well, thank you very much. That was really interesting. We did have one question in the chat here, and then anybody else who has any, feel free to put it in there and we'll share. Are you doing any 3D mapping?
In several 3D questions on 3D mapping, in several senses, we do use our line data, because we do have vertical control as well as horizontal. We absolutely can plot and do plot our line data in 3 dimensions to understand the vertical relations between the passages, or the relations between the passages and the overlying topography as well. In addition, we have used LiDAR in several caves and in several areas to build 3-dimensional point clouds, and to a much more limited extent, photogrammetry for development of 3-dimensional point cloud data in the park as well. And we do link, and I should note, we use both airborne LiDAR topographic surveys for identifying potential cave entrances and for developing the topography, but also when I mentioned LiDAR, I also mean on the ground stand-up LiDAR unit scanning cave passages for documenting those cave passages. So we use both airborne LiDAR and on the ground LiDAR on tripods in cave passages.
So, and then as a follow-up to that, do you include the lithology in the 3D? Are any of these available?
None are currently available at the moment. And actually, one of the more interesting ones recently in 3D is we've used photogrammetry for documenting some very interesting shark fossils in the cave walls at Mammoth Cave, trying to get a three-dimensional reconstruction of this fossil that cannot readily be removed, of these two fossils that cannot readily be removed from the cave because of difficulties of getting materials to them that would allow them to be removed. So we're using the three-dimensional very selectively. We've also just recently been working on on a plan to upgrade one of our tour trails, and our architecture and engineering company just did a LiDAR scan of our existing trail for us to visualize what we can do in upgrading that trail, but it's not something that's available to the public yet.
Okay. And then are your expeditions to do this mapping manned by volunteers or paid staff?
The Cave Research Foundation is our primary people doing our cave mapping and expedition, and it is 100% volunteer. They have no paid staff, and the park has no staff who are actually paid to be doing cave mapping. I work with them and I interface with them as part of my job, but when I'm in there with them mapping, I'm on volunteer time. Okay.
Do you have any plans to create more maps using GIS? Do you use non-Esri mapping or surveying applications? So what are they using?
Currently, our primary, we primarily use Esri products currently on park for most of our mapping. The Cave Research Foundation uses, and the cavers have developed some data reduction software that is non-Esri, and actually most of the mapping, the drawing of the maps is actually done in Illustrator, or occasionally some of our cartographers prefer drawing in CAD as well. Most of our
and
park.
then you bring those into Esri.
And then, yes, and then we import those into GIS as well. Fortunately, the data reduction softwares that cavers have built are also meant to be able to be used with GIS. So they export either KMLs or shapefiles or both. Let's see. Oh, did you read that? She shared that if she had seen it in 3D, she might not have done that trail because it was narrow and steep and stuff. Yep.
Yes.
We do want to develop some of that so that we can let visitors know more what to expect on their trails. And there are several national park caves, actually Timpanogos and Lehman Cave, both recently have put out very nice three-dimensional LiDAR walk through, explore the cave
like virtual tours?
Virtual tours on that are available on their websites.
Okay. Very good. I don't anything else in the chat here. If anybody else has a question, if they could put it here in the chat, we'll address that. And barring nothing, we'll move on to the next activity for the day. Let's see. Okay.
In many ways, the cave environment is the biggest limitation on what technologies we're able to use. There are lots of things that work really nicely in big, dry, upper level passages, but when you move them down in passages that you're surveying in inflatable kayaks, you get really worried about taking some of that expensive technology down when you're sitting in an inflatable kayak.
All right. Well, that was very interesting, and we thank you for your time and joining us for our first virtual GIS day. And
very much enjoyed it. Hope everyone is having a good GIS day.
Great. Thank you so much.
I'll stop my share.
Okay. All right. All right. So you should take a little break and make your way over to a session here now at 1 o'clock, and you have a choice of 4 different tracks for that. So thank you very much.